last video of this course, we are going to discuss natural deduction for predicate logic. We are going to discuss what it means to prove something and how can we modify natural deduction to work for predicate logic. First, we need to define what it means to prove and what kind of object we wish to prove. First, consider this formula. Note that the variable y is not specified. We call such a variable a free variable. And this formula is not something you can prove because it just cannot be neither true nor false because it depends on y. For different y's it's true, and for some of them it's false. This formula, from another point of view, is better because y now is somehow specified. We know that it's under the existential quantifier. But this formula is not something also we wish to prove because we know that for different substitution for r and for the domain, we can make this formula true and false. So we don't know how to prove this. And moreover, we're not going to try to do this. And the last formula is an example of a sentence we wish to prove. First of all the variables are specified. Secondly, it's true whenever r we choose and whenever the domain we choose. Because it's easy to see that if this is true, then we can choose y here be equal to x, and this would be true as well. The formula is like this. We are going to call logically valid. So definition, a formula phi is logically valid if there are no free variables and in any structure the formula is true. So in order to allow natural deduction to work with predicate logic, we allow it to use predicate formulas instead of propositional formulas. And we also add 4 new rules, 2 for each quantifier. For universal quantifier, we add these 2 rules. So if you have somewhere a of x, you can replace this x by y and add the universal quantifiers in front of it. And similarly, if you have universal quantifier by x and after that a of x, you can replace this by a of t, where t is any term whatsoever. There is only one restriction here. X shouldn't be a free variable of any open hypothesis. Similarly, for the existential quantifier, we add 2 rules. One of them is introduction and the other one is elimination. So if you know that a of t, where t is some term inside of the formula, you can replace this term by a variable x and add the existential quantifier. And finally, the elimination of the existential quantifier is the following. You know that exists x, a of x, and you also know that if you have a of y, where y is some variable, you can derive b. Then, using these 2, you can derive b. And there is again a small restriction. Y shouldn't be a free variable of b or any hypothesis open here. Let's illustrate these 4 new rules by proving that a logically valid formula we mentioned before is actually logically valid. Let's prove that for all x, r of x, x implies that for all x exists y, R of xy is actually logically valid. So we start with an empty assumption, and since we're going to prove the implication, we assume this. After this, we need to remove this x in order to insert exists y in the middle. In order to remove existential quantifier, we can use elimination of the existential quantifier, and we can replace the variable by any term. We're going to replace it by the term x itself. So we get R of x using the elimination of the existential quantifier applied to the row 1. The next step, we need to replace this x by y and add the existential quantifier. So we need to derive something like this. And can be done by the introduction of the existential quantifier, because we can replace any term by a variable and add the existential quantifier in front of it. And in this case, we replace the term x in the second position by the term y, by the variable y, and add the existential quantifier. So it's introduction of the existential quantifier applied to the row 2. Now we need to put back the universal quantifier. So we need to derive for all x exists y, R of xy. And in order to add a quantifier, we need to use the introduction rule. So this rule. So we can replace every occurrence of x by y and add the universal quantifier. In this case, we have this variable x, we replace it by for all x, x. And finally, we prove that under this assumption, we can derive this. So the implication is true by the introduction of the implication. So for all x, R of x implies for all x exists y, R of x, y, by the introduction of the implication applied to the row 4. And here I forgot to write it. It's introduction of the universal quantifier applied to the row 3. Like in the propositional case, in the predicate case, we have two theorems that are proving soundness and completeness of this system. First of them is soundness. It says that if you have a predicate formula and there is a proof of it, then this formula is logically valid. And the second theorem says that if you have a predicate formula and it's logically valid, then there is a proof of this formula. In this video, we finished the discussion of predicate logic, and as a result, we finished discussion of the basics of mathematical logic. If you have any questions, ask them in the comments. Thank you for watching.